The aircraft that looked slow and awkward was one of the first targets the Japanese tried to knock out at Pearl Harbor. Why? Why did a flying boat, looking more like a heavy seabird than a weapon, become almost as dangerous as battleships and airfields? Why were its moorings hit as if one of the American fleet's most important weapons was sitting right there on the water? And why was this same machine later trusted with secret diplomacy, platinum, polar routes, and the rescue of men stranded in the middle of the ocean? The Catalina was not the fastest aircraft of the war. It was not the most beautiful. It was not built for spectacular air duels. But it was feared where speed did not decide the outcome, where the ability to see first mattered more. This machine became so necessary that it was bought, copied, modified for local conditions, and kept in service for decades. So we are not looking at just a successful aircraft. We are looking at a machine enemies tried to blind before takeoff, allies used for the most dangerous missions, and the ocean tested harder than any proving ground. Today, we will open the story of the Catalina without parade gloss, from its first trials in Soviet trace to Pearl Harbor, secret flights, and rescue missions where this quiet flying boat became the last chance. Watch to the end, and you will understand why one of the slowest machines of the war became one of the most dangerous machines of the ocean. In the late 1920s, behind the doors of Consolidated Aircraft in California, a project was being prepared that looked as if it had already earned its place among serious military machines. Drafting tables were covered with plans, load diagrams, range calculations, structural schemes, and figures meant for men in uniform, not for exhibition halls. The company was not playing with an elegant aviation toy. It was building a long-range bomber, a machine that was supposed to impress the military and bring Consolidated a heavy contract. The aircraft received the dry index S-372. No romance, no heroic name, no legend yet. Just an industrial code, the kind of code that can hide years of human labor behind a few cold characters. Engineers worked on it for more than a year, and they had every reason to believe they were not wasting their time. On paper, the machine looked strong. It promised long range, serious speed, respectable payload, and the kind of structural reserve that military officials always demand and then pretend not to notice when they choose someone else. Consolidated believed it had built a worthy competitor. But military procurement has never been a clean contest of pure engineering. It is often a brutal table game where timing, influence, internal preferences, and hidden priorities sit next to numbers. This applies to the ugliest moment in any design bureau. The aircraft exists, the calculations exist, the effort has been spent, the team has burned through months of work, and then the door closes. Not because the machine is useless, not because the engineers failed, but because another project gets the signature, the money, and the future. Consolidated lost. The contract went to another company. Another aircraft moved toward production. Another team heard the pleasant noise of victory, and S-372 remained on paper. More than a year of labor was suddenly reduced to folders, drawings, and a painful question. What do you do with a good machine that nobody bought? That is where the real story begins. Not with applause, not with a parade, not with an admiral shaking hands for the cameras. It begins with a failure that could have quietly buried the whole effort. Most companies would have done exactly that. Close the files, move the engineers to another assignment, and pretend the expensive disappointment never happened. But Consolidated did not treat the failed bomber as garbage. That was the important decision. The company looked at the rejected work and understood something cold and practical. A lost competition does not always mean a lost aircraft. Sometimes it means the aircraft was built for the wrong question. This applies to the kind of engineering stubbornness that separates ordinary factories from companies that leave a mark on history. Anyone can celebrate a contract. Far fewer can stand over a rejected project and ask a dangerous question. What if these drawings are not a failure, but a weapon waiting for another battlefield? The key was not sentiment. It was not pride. It was calculation. The range work, the structural thinking, the load capacity, the general layout, the understanding of long flights, all of this could be used again, not as a bomber, but as the foundation for something the Navy would soon need badly. For several years, those ideas stayed in reserve. They were not a glorious success, but they were not a corpse of engineering either. They were stored experience, and experience is too expensive to throw away. Then, in the early 1930s, the United States Navy opened the door to a new requirement. The Navy needed a patrol flying boat, not a delicate aircraft tied to a clean runway, not a short-legged machine that had to stay close to shore. It needed an aircraft that could take off from water, land on water, cross thousands of kilometers without refueling, and operate where concrete strips simply did not exist. This applies to the point where the failed bomber project suddenly became valuable again. The ocean demanded the very qualities Consolidated had already worked on: range, endurance, payload, structural strength, and the ability to support long missions. What had not been enough to win one competition now looked like the raw material for a completely different aircraft. So the old folders came back to life. The engineers did not copy them blindly. They reworked them, reshaped them, and forced the old logic to serve a new master, the sea. A bomber that had not entered production became the hidden ancestor of a flying boat that would later patrol oceans, rescue crews, and make enemies nervous from thousands of kilometers away. There is a harsh lesson here, and official histories usually soften it too much. Great machines are not always born from clean victories. Sometimes they rise from rejection, embarrassment, closed doors, and the refusal of stubborn people to throw away a good idea just because a committee said no. While someone else celebrated the old contract, Consolidated was unknowingly preparing a machine for another kind of war, a war where speed alone would not be enough, a war of distance, water, fatigue, patrol lines, missing targets, stormy landings, and crews who needed an aircraft that could stay out there when others had already turned back. That is why the failure of S-372 was not the end of the story. It was the first hard strike of the hammer. The aircraft lost on paper, but its ideas survived. And from those rejected ideas would come the beginning of the Catalina, a machine that proved one brutal truth. In aviation, the loser of one contest can become the master of an entire ocean. The United States Navy needed an aircraft that could not be squeezed into the limits of ordinary aviation. Not a graceful machine for a dry runway, not a short-legged scout chained to the shoreline. It needed an aircraft that could rise from water, return to water, and go beyond the horizon where there was no concrete strip, no backup field, and no room for weak construction. That was when the old Consolidated drawings stopped being the remains of a lost contest. They were placed back on the tables, but now the engineers looked at them differently. What had once been prepared for a long-range bomber was forced into a naval problem. This was not a beautiful gesture by desperate engineers. It was cold calculation. If the Navy needed a long-range flying boat, then the rejected work could still strike back at the competition. This applies to the moment when an aviation failure turns into industrial revenge. Yesterday, the project had been unwanted. Today, its ideas were being measured against the ocean. Where one committee had closed the door, the Navy suddenly opened another. The future aircraft could not be just a normal airplane with floats. The Navy did not need that kind of primitive compromise. It needed a real flying boat, a hull built for water, range fit for ocean patrol, and strength capable of surviving a hard landing on waves. War at sea does not forgive office fantasies. Out there, every weakness turns quickly into disaster. Consolidated engineers took the old foundation and changed its purpose with brutal discipline. Aerodynamic calculations, structural thinking, long flight ideas, layout solutions, everything was used. But now gravity was not the only enemy. Water became the second enemy, heavy, treacherous, salty, merciless to weak metal, and foolish design. This applies to the main difference between the new machine and an ordinary aircraft. A normal aircraft can be excellent in the sky and helpless on water. A naval flying boat must be strong in two worlds at once. It must fly like an aircraft, sit on waves like a boat, and refuse to fall apart when nature decides to test it. That is how the new military index appeared, XP3Y1. Dry, faceless, almost bureaucratic. No name, no glory, no Catalina. Only the designation of an experimental patrol aircraft for the Navy, as if this were not the beginning of a future legend, but just another line in a dull technical report. But behind that cold index, a dangerous machine was already taking shape. It had not yet received a name, but it already carried what would later make it famous. Range, maritime toughness, the ability to operate far from shore, and independence from ordinary airfields. For the Navy, this was not convenience. This was power over the empty spaces of the ocean. This applies to the unpleasant truth often forgotten by admirers of shining fighters. Ocean war is not won only by those who rush beautifully into attack. It is won by those who see farther, remain longer, and notice danger first where everyone else sees only a horizon. XP3. Y1 did not look like a hero for the front page. It did not promise insane speed, dizzying turns, or glamorous air duels. Its strength was rougher and more practical. It had to stay over water for hours, search for targets, carry a load, return, and be ready to take off again. And this is where the skeptics run into the hard part. The nameless machine already had what many loud projects lacked, a clear purpose. It was not being shaped for a pretty figure in a sales brochure. It was being built for a real naval need, for a war of distances, for operations in places where a mistake by a pilot, designer, or mechanic could cost a crew its final chance. This applies to the core of the future Catalina. It was not born as an aircraft of vanity. It was born as a tool, a large, rough, long-range, sea-going tool that would become the eyes of the fleet and the rescuing hand for men whom the ocean had already begun to claim. While the documents still carried only an index, the design already revealed its future. High wing, boat-shaped hull, long-range logic, water landing, patrol mission, all of it formed one formula. The formula of a machine that did not need to please the public, but had to obey orders where other aircraft became useless. No romance, only an index. But this is how the most dangerous technical biographies often begin. First, a faceless line in the paperwork, then a test field, then the first order, and then everyone discovers that under a boring designation, there was an aircraft destined to outlive its critics, its rivals, and even an entire era. During the trials, XP3Y1 had to prove one simple thing, that it was not an expensive fantasy from a drafting room. The Navy did not need beautiful promises or polished talk about a glorious future. Sailors needed a machine that could rise from water, go far beyond the horizon, return, and refuse to fall apart under the first serious test. And here, the nameless flying boat began to answer not with speeches, but with numbers. Its range was about 4,800 kilometers. For an aircraft of that period, that sounded almost insolent. Such a machine could cover a distance comparable to flying from London to New York without landing and without refueling. Not a short hop along the coast, not a pleasant run over a harbor, but real ocean reach. This applies to the future Catalina's main weapon, range. In naval war, the side that sees farther gets the chance to strike earlier, warn earlier, and rescue earlier. If an aircraft can stay over water for hours, it stops being just a vehicle or a scout. It becomes the long arm of the fleet. Its cruising speed was about 160 kilometers per hour. For admirers of fast fighters, that might have looked almost laughable. But the Navy was not looking for an aerial racer built for elegant turns. It needed a machine that could slowly, stubbornly, and methodically sweep huge stretches of ocean, where speed often matters less than endurance, range, and the ability to stay on course. Its maximum takeoff weight reached 11,340 kilograms. That was not a light showpiece with wings. That was a heavy maritime aircraft capable of carrying fuel, crew, equipment, useful load, and everything required for long work far from shore. In such figures, there was no romance. There was harsh military accounting. This applies to what military buyers understand better than casual observers. An aircraft is not valued only for the beauty of its silhouette or the thrill of its speed. It is valued for what it can carry, how far it can go, and whether it can carry out an order in a place where help is not coming. Naval officers looked at the test results and understood that they were not watching another experimental toy. They were looking at a machine that filled a painful gap in fleet capability. The ocean is enormous, airfields are few, ships move slowly, and reconnaissance is needed immediately. Then suddenly an aircraft appears that can take off from water and work where ordinary aviation remains chained to land. That is why the Navy's decision was sharp. It did not wait for the full end of the trials. It did not spend months passing papers from office to office. It did not drown the machine in endless meetings for the sake of neat procedure. The order was placed while testing was still underway. The aircraft was still proving itself, and the contract already said one thing clearly: the Navy wanted it. This applies to the rare case when a machine makes military men hurry. Usually the customer is cautious, demanding, and suspicious. He likes to request, test, delay, modify, and test again. But here the Navy saw a combination of qualities that could not be left to rivals or buried in bureaucratic mud. That does not happen by accident. Military organizations do not hand out trust as a courtesy. They do not place an early order simply because engineers tell a pleasant story. If an aircraft draws serious naval interest during trials, it means the Navy has seen not a promise, but a tool. And this tool was dangerous precisely because of the ocean. It was not meant to win glamorous air duels. It was not meant to dive into battle like a predator. Its job was rougher and more important. Search, observe, remain on station, and serve at distances where the human eye fails and the map becomes an empty blue sheet. This applies to the first real victory of XP-3Y1. It did not yet carry the name Catalina. It had not yet become a legend of rescue operations. It had not yet met its war, but it had already proved the main thing. The fleet needed exactly this kind of machine, not someday, not after years of hesitation, but now. That was the power of the trials. They removed uncertainty from the project. Before them, the Navy had an experimental flying boat with a dry index. After them, it had the beginning of a long-range maritime observation system, and that changed the value of the entire machine. The nameless aircraft passed its first serious judgment not in newspapers and not in polished office promises, but on water and in the air. It showed range, weight capacity, sound design, and the ability to solve a real naval problem. After that, the Navy did not wait, because waiting for such a machine meant leaving the ocean blind by choice. An ordinary aircraft depends on a runway, concrete, markings, airfield crews, a smooth surface, and dry ground under the wheels. That is the difference between comfortable aviation and naval aviation, where no runway is waiting, no controller can calm the crew, And under the belly of the machine, there is not an airfield, but the ocean. For the Catalina, this was not a decorative feature. It was the central verdict of the design. The aircraft had to live in two elements at once. It could not be designed as an airplane with a boat bottom simply attached to it. Water exposes that kind of fraud quickly. A wave strikes without respect for engineering ambition, salt water pushes into every seam, and a hard landing on a crest can turn a proud drawing into a shameful pile of metal. The Navy did not need a toy with wings. It needed a real flying ship. This applies to the harshest task of the Catalina. It had to land where an ordinary aircraft became helpless, not on a smooth runway, not on a quiet, prepared surface, but on living water that rolls, hits, rises, breaks, and can strike the hull from below at any moment. Consolidated engineers understood one ugly fact. If the hull was weak, range, payload, and fine performance figures would be empty boasting. An aircraft may travel thousands of kilometers, but what is the point if, after a rough landing, it begins to sink like a rotten boat? So the hull was not treated as a shell. It was treated as a survival system. Inside, it was divided into 5 watertight compartments. That was ship logic, rough and intelligent. If water breaks into one compartment, it must not be allowed to wander freely through the whole hull. It stays in the damaged section while the rest of the machine remains afloat. For an aircraft, this was almost defiant. Aviation was taking an old naval principle of survivability and turning it into its own weapon. This applies to the situation where seconds become more valuable than any technical elegance. A damaged hull does not yet mean the crew is lost. A flooded compartment does not yet mean the aircraft is finished. If the Catalina stays on the surface, the men get time, and time in the ocean is a chance. Here is the real price of engineering, not in advertising shine, not in polished phrases about advanced solutions. The price is in the fact that after an impact, damage, or hard landing, the machine does not have to go under immediately. It can hold. It can give the crew minutes, sometimes hours, to call for help, prepare emergency gear, move into rescue equipment, or wait for a ship. The Navy understood perfectly that the ocean does not forgive the weak. At sea, there is no roadside ditch where a failing aircraft can roll away. There is no field where it can be put down on its belly. There is only water to the horizon, wind, waves, and the cold indifference of nature. That is why every internal bulkhead inside the Catalina was not a technical detail. It was insurance against instant loss of the aircraft. This applies to a principle often missed by people who look at aircraft only from the outside. A beautiful silhouette means nothing if there is no survivability inside. A successful wing shape means nothing if the hull cracks after a wave landing and starts taking in water. The Catalina was not built for a showcase. It was built for bad weather, long routes, and ugly incidents that official reports usually describe in dry lines. The hull of a flying boat had to do more than carry the crew and equipment. It had to cut water during takeoff, absorb impact during landing, avoid digging in with its nose, avoid rolling over, and avoid behaving like a heavy cabinet thrown into the sea. It needed something of an aircraft and something of a ship. That combination made the Catalina dangerously useful. An ordinary aircraft forgets the ground after takeoff until the next landing. The Catalina could not forget water for a single minute. Water was its starting field, its emergency chance, its operating environment, and its chief examiner. Every frame, every joint, every curve of the hull had to answer one question: will the machine withstand the ocean when everything goes wrong? This applies to the part of military technology that does not appear in parade photographs. No weapon shines there, no threatening cannon sticks out, no sharp fighter profile catches the eye. But that is where the crew's return is decided. An internal partition, a strong hull, the right landing shape of the bottom. All of this sounds boring only until the aircraft is sitting on a wave. The Catalina was built around this crude truth. If you work over the ocean, you have no right to be merely an aircraft. You must be a boat, a ship, a shelter, and a final chance at the same time. That is why its construction was not an engineer's whim. It was a hard naval necessity translated into aviation language, and when the Navy looked at this machine, it did not see only wings and engines. It saw an aircraft that could not only fly far, but survive where others would become useless weight on the water. That was the first real strength of the Catalina. It did not argue with the ocean in beautiful words. It was built to take the blow. The Catalina was not built for a short dash out and back. It was not shaped for a pretty flight of a few minutes, where the pilot could show the aircraft, turn around, and return to a warm airfield. This was a machine for a different kind of punishment. Long ocean patrols, with water under the hull for hour after hour, only a horizon ahead, and fatigue becoming an enemy as real as weather or engine trouble. That is why the aircraft carried a set of features that could look almost domestic from the outside. Trim tabs, a galley, bunks, a high wing, retractable wingtip floats. None of that sounds as loud as guns, bombs, or speed. But in real naval war, such details could matter more than a proud figure in a brochure. A pilot too exhausted to hold the controls properly can turn even a fine aircraft into a dangerous box of metal. This applies to the brutal truth of long-range patrol. The man inside the machine matters as much as the engine outside it. If the crew is drained, if hands go numb, if eyes begin to close, if men cannot relieve one another and recover strength, range alone becomes useless. An aircraft can look impressive on paper, but the ocean does not test paper. It tests living people. Trim tabs on the control surfaces were not luxury, and they were not a toy for comfort. These small surfaces reduced the force needed on the controls and helped the pilot avoid fighting the aircraft every minute of the flight. On a short mission, that might sound minor. On a patrol lasting many hours over water, it becomes a matter of control, accuracy, and endurance. Picture not a parade flight, but a heavy watch. Engines drone steadily, the hull vibrates, instruments demand attention, gray ocean sits behind the glass, and it continues hour after hour. The pilot has no right to relax, but he is not made of steel. That is why the engineers had to think not only about the wing and the hull, but also about how a human being would survive the flight. This applies to the kind of design decision that does not look heroic until you are inside the cockpit. A trim tab does not create triumphant headlines, but it can preserve a pilot's strength for the moment when he must land on water, search for a target, escape bad weather, or make a decision with the fuel running low. The galley and the bunks looked even more provocative for an aircraft of that period. Real ship logic inside an airplane. Not a whim, not comfort for a spoiled crew, but a cold understanding of the mission. If the aircraft was expected to remain in the air for many hours, the crew had to eat, rest, rotate duties, and keep the ability to think. In an ordinary aircraft, a bunk could look almost absurd. In the Catalina, it was a weapon against exhaustion. One crewman watched instruments while another rested. One stayed at his station while another recovered strength. On paper, it sounds like simple crew management. Over the ocean, that detail separates a functioning crew from men acting on their last reserve. This applies to flights where time stops being an abstract word. 20 hours in the air is not a pretty line for a report. It is noise in the head, vibration in the bones, salty dampness, strained eyes, and endless water beneath the hull. Under those conditions, hot food and the chance to lie down for a short time are not comfort. They are the preservation of combat effectiveness. The high wing was not a designer's whim either. It kept the engines higher above the water, protecting them from spray during takeoff and landing. In a calm photograph, this looks simple. In reality, spray, waves, and salt water could become enemies as serious as enemy fire. An engine that swallowed the wrong water could turn a long patrol into a fight to get home. The retractable wingtip floats solved another problem. On the water, they helped the aircraft remain stable, avoid rolling to one side, and keep a wing from catching a wave. In the air, they retracted and became part of the wing, avoiding unnecessary drag. A simple solution? Only if spoken casually. In practice, it was an attempt to force one machine to be stable on water and cleaner in flight. This applies to the central engineering compromise of the Catalina. It had to be a boat when it touched water and an aircraft when it climbed into the sky. Too much boat meant lost speed and efficiency. Too much aircraft meant dangerous weakness on the water. The engineers searched for the middle ground, and that middle ground made the machine so useful. The whole construction carried one blunt idea. The crew had to reach the end of the mission, not take off beautifully, not impress spectators, but endure the route, return with information, bring people back, land on water, and be ready again after service. The Catalina was a working machine of war, not an aerial pose built for a parade. That is why its long flight design was more honest than many louder military projects. There was no empty shine in it. There was an understanding that war over the ocean is not only attack and not only courage. It is duty shifts, exhaustion, food on board, narrow bunks, heavy controls, a wet hull, spray under the engines, and many hours during which the machine must remain obedient. This was where the Catalina began to show its true character. Not predatory, not theatrical, not designed for instant admiration. It was built for long work, for patience, for exhausting routes where weak decisions reveal themselves quickly. The longer the flight lasted, the clearer it became. The Navy was not looking at just an aircraft, but at a long-range maritime instrument built around men, water, and time. The first production Catalinas were not yet the steel ocean instrument that fleets would later remember. This was a machine that matured quickly under the pressure of real tasks. In aviation, that does not happen often. A weak design is usually tortured with endless corrections, while a strong one is strengthened, enlarged, equipped with new possibilities, and sent where yesterday it still seemed too bold. The Catalina followed the second path. First, it needed engines capable not merely of lifting an aircraft, but of dragging a heavy maritime machine out of the water with crew, fuel, equipment, and useful load on board. Taking off from a runway and taking off from water are two different worlds. A runway does not grip the hull, does not strike with waves, does not slow the bottom, and does not throw spray into the engines. Water does all of that at once. This applies to the crude physics that no fine slogan can defeat. If the engines are not enough, a flying boat becomes helpless weight on the surface. It accelerates too slowly, lifts off too heavily, loses safety margin, and forces the crew to hope that wave, wind, and load do not meet at the worst possible moment. So the strengthening of the engines was not a chase after a pretty figure. From the second series, the Catalina received two Pratt & Whitney R-1830-6 engines, each producing 1,000 horsepower. 2,000 horsepower in total was not a matter of prestige. It was the question of whether the aircraft could leave the water with confidence and carry its duty far from shore. Then came the next step. From the third series, the machine received R-1830-92 engines, each producing 1,200 horsepower. An increase of 200 horsepower per engine looked like a dry line in the documents, but behind it stood real military value: more pull, more confidence on takeoff, more room for load, and a better chance of returning from a distant mission. This applies to the central principle of the Catalina's development. It was not being turned into an aerial record breaker for newspaper applause. It was being made heavier, tougher, and more suitable for dirty work over the ocean. Every new engine was not decoration. It was an answer to a hard question. Can the machine carry more, go farther, and endure worse? But engines were only one side of its growth. The other side was the hull. Early aircraft still carried the marks of compromise, metal in load-bearing elements, fabric in parts of the skin. That made sense for its time, but the sea quickly teaches engineers that lightness without durability can become an expensive mistake. Moisture, salt, heat, changing temperatures, all of it works against weak material every day. By the beginning of the 1940s, the hull had become fully metal. This was not a minor technical update. It was a change of class. Metal tolerated the maritime environment better, carried loads better, and suited a machine that had to live among spray, fog, wet bases, long routes, and rough servicing. The Catalina was shedding the traits of an early compromise and becoming a true military tool. This applies to the part of aviation where romance ends quickly. Fabric looks charming in stories about early aircraft, but the ocean does not read charming stories. It does not care how beautiful a machine looks in a photograph. It tests seams, rivets, skin, strength, corrosion, and the ability of a hull to survive one more day of service. The size of the machine also grew with the tasks. The Catalina was expected to carry more fuel, more equipment, more useful load, and more hours in the air. War did not ask whether designers found that convenient. The fleet wanted an aircraft that could search for ships, escort convoys, patrol empty squares of ocean, and stay where ordinary aviation ran out of breath too soon. And then came the detail that changed the meaning of the whole machine: radar. Not a shiny device for a report, but a rough instrument of military sight. It allowed crews to search where earlier they saw only fog, night, rain, and the gray wall of the horizon. A ship in dawn haze, a shape on the water, a submarine trace, a periscope, a conning tower, a suspicious mark on the surface, all of that stopped depending only on the human eye. This applies to the moment when the Catalina stopped being merely a long-range patrol aircraft. Range alone was already a frightening advantage. But range combined with radar turned the aircraft into the real eyes of the fleet. It could remain over the sea for hours, examine huge areas, and find what the enemy hoped to hide behind night, weather, and distance. Before that, the ocean had been a convenient shelter. Vast water concealed ships, routes, submarines, convoys, and movement traces. Whoever remained unseen had the chance to strike first or escape without punishment. A radar-equipped Catalina broke that logic. It pulled a target out of emptiness, gave coordinates, warned the fleet, and turned endless water into observed territory. That is why the combination of engines, metal, and radar mattered far more than a simple list of specifications. Engines gave pull and load. Metal gave strength and endurance. Radar gave sight. Together, they created not just a flying boat, but a machine of ocean war, able to operate at distances where commanders had once almost guessed from maps. This applies to the boldest fact of the whole design. In the early 1930s, there were no computer models, no digital simulations, no familiar modern calculation programs. There were pencils, drafting boards, logarithm tables, engineering discipline, and cold minds. And from that set came a machine that did not need to be thrown away after the first checks. It was not rebuilt from nothing. It was developed. In aviation, that is rare. Very often, the first version is only a rough draft, later cut, patched, made heavier, and rescued by compromise. The Catalina was different. Its basic formula was so accurate that later series did not deny the original idea. They strengthened it. More powerful engines, a stronger hull, more possibilities, new equipment, all of it fitted onto a successful skeleton. That is how a nameless machine with a dry index became what the war would later recognize. Not the fastest, not the most beautiful in the eyes of air duel admirers, but dangerous precisely because of its usefulness. It could take off from water, go far, carry load, see through bad weather, remain over the ocean, and return with information for which a fleet would pay any price. The Catalina did not mature for parade duty. It matured for night, fog, storm, long patrol, and war in which the enemy hopes not to be seen. And the stronger the engines became, the tougher the hull grew, and the more confidently radar worked, the clearer it became. The Navy was no longer looking at an experimental flying boat. It was looking at the future master of ocean reconnaissance. America could not keep the Catalina story entirely to itself. The machine was too visible in its usefulness, too blunt in its advantages, too clear in what it offered where other aircraft ran out of options. When an aircraft can remain over water for long hours, land where there is no runway, and work in weather that exposes weaker machines, foreign militaries will inevitably look at it. The Soviet Union looked. The trigger was the Arctic. Not an office, not an exhibition, not a polished, consolidated brochure, but an icy space where machines quickly stop pretending to be good. There are no gentle conditions there, no beautiful airfields, no mercy for a weak design. There is ice, fog, wind, snow haze, water, and distances that break arrogance. This applies to the search for Sigismund Levanevsky. The Soviet pilot disappeared during a flight over the North Pole, and the mission itself was already a challenge to the age. A polar flight was not a newspaper adventure. It was a harsh test of crew, communication, navigation, and structure. When contact was lost, a search operation began, and it needed machines, not slogans. An American civilian consolidated flying boat was brought in for the search. It was called Hercules, and Soviet specialists did not see it as foreign curiosity. They saw a practical answer to a very unpleasant question. How do you search for people and aircraft in places where ordinary aviation quickly reaches its limits? In the Arctic, this machine was no longer a drawing and no longer a promise. It was working. And here begins the part usually softened in official language. Soviet aviators saw how the flying boat behaved in conditions where weak projects quickly collapse. In fog, among ice floes, over cold water, in wind and poor visibility, it kept operating. It could land on water, take off from water, and carry out long search routes where every mistake carried a hard price. This applies not to curiosity, but to military pragmatism. Soviet specialists did not need to fall in love with a foreign aircraft. They had to understand whether it contained a solution that their own fleet and polar aviation lacked. The answer was unpleasantly clear. Such a machine was needed. Levanevsky was never found. But the Arctic operation revealed something else. A vast country with seas, polar regions, distant coasts, and a limited airfield network needed a flying boat of this class, not a parade ornament, not a rare imported specimen, a working aircraft able to connect sky, water, and frozen emptiness. In 1937, the Soviet Union bought a license to produce the machine. That was a strong move, even if it did not sound comfortable for a proud aviation power. Buying a license meant one simple thing. A domestic aircraft of the same level either did not exist or did not solve the task as required. That is not humiliation. That is the cold logic of a state that needs equipment, not beautiful excuses. This applies to the kind of case where pragmatism matters more than pride. The authorities could have pretended for years that everything already existed. They could have criticized the foreign design while hiding the weak points of their own school. They could have lost time while the fleet and polar routes waited for a real machine. Instead, they chose to buy the license and master production. Production was organized in Taganrog. This was no longer a story about one purchased aircraft to admire and park in a hangar. It was about the right to build the machine independently, study its construction, adapt it to local conditions, and place it inside the system of Soviet naval aviation. Soviet engineers gained the chance to take apart someone else's solution down to its underlying logic. It must be said directly, that purchase was a recognition of the strength of Consolidated's design. Not political sympathy, not advertising noise, not a passing impression. The strength of the design. The Catalina and its related flying boats showed that they could operate in places where theoretical performance talk ends and rough service begins. This applies to the real value of Arctic experience. On a drawing, many things can be promised. On a test field, a machine can look respectable. But when an aircraft works for months among ice, fog, and wind, it can no longer be judged only by its specification sheet. It either carries the service, or it becomes a burden for those who trusted it. Soviet interest in the Catalina was therefore neither accidental nor romantic. They saw in this machine a tool for a huge country, for the Baltic, the North, the Black Sea, the Pacific, polar routes, and remote bases. For places where water replaces the runway, where weather dictates terms, and where an aircraft must be not only fast, but patient. The license purchase became one of the most revealing episodes in the machine's biography. An American design, born from old drawings and a naval requirement, suddenly became necessary to a country building its own powerful aviation school. But that was precisely the strength of the Catalina. It crossed ideological walls, not with speeches, but with work. That is how the Soviet trace entered the history of this flying boat. Through the Arctic, through a missing crew, through a hard search, through cold analysis of what had been seen. Not a parade, not a diplomatic gesture, not an aviation fashion. A severe conclusion by people who saw the machine in real conditions and understood. This aircraft should not be discussed endlessly. It should be obtained. Buying the license was only the beginning. The real test did not start in an office where papers were signed, and not during a formal display of foreign equipment. It started in the factory, at the machines, inside workshops, among drawings, tolerances, materials, working hands, and engineering arguments. It is one thing to admit that an aircraft is needed. It is another thing to force it to become your own. Production of the licensed flying boats was organized in Taganrog. This was not a simple act of copying. Soviet industry had to master a foreign design, understand its logic, transfer it into its own production conditions, and make sure that the aircraft did not remain an overseas visitor, but entered fleet service as a normal working tool. For naval aviation, that mattered directly. The country needed not a curiosity, but a fleet of machines. This applies to the moment when foreign equipment stops being a subject of interest and becomes a military necessity. While an aircraft stands in a hangar as a sample, it is interesting to engineers. But once it enters service, it is judged by mechanics, crews, unit commanders, and the people who must send it out in bad weather. The Taganrog plant built around 150 of these flying boats. Another roughly 250 aircraft arrived through Lend-Lease. In total, the Soviet fleet received about 400 aircraft of this type. That was no isolated episode, no accidental purchase, no diplomatic souvenir. It was the full inclusion of the machine into the system of naval aviation. And the scale matters. 400 aircraft for a vast country with seas, fog, remote bases, northern routes, and a Pacific coastline was not luxury. It was an attempt to close a real gap in fleet capability. The sea demands constant presence, and ships cannot be everywhere. A flying boat gave the fleet something especially valuable in difficult geography: flexibility. This applies to Soviet conditions in particular: the Baltic, the North, the Black Sea, the Far East. Different conditions, different weather, different infrastructure. In one place, dampness and fog. In another, cold. Elsewhere, long distances or a base without enough airfield support. Under such conditions, an aircraft that can operate from water stops being exotic. But Soviet engineers were not going to worship the American design. They took it apart, studied it, tested it, and began adapting it. The most noticeable decision was replacing the engines with domestic ones. Instead of depending on supplies from across the ocean, they chose their own engine, familiar to their industry and their mechanics. This meant the M82FN engine designed by Arkady Shvetsov. At first glance, the decision looks strange. Why replace something that already works? But military operation does not tolerate naive questions. An engine is not just power on paper, it is spare parts, repair, trained mechanics, storage, maintenance at remote bases, and the ability to return an aircraft to service quickly. In a major war, an aircraft dependent on foreign supply always remains vulnerable. This applies to the main principle of Soviet adaptation. Equipment must be serviceable where it serves. If an aircraft stands at a distant base, surrounded by damp air, wind, salt water, and shortage of time, nobody will wait for perfect conditions. A mechanic must understand the engine, have access to parts, and know what to do without elegant factory presentations. A domestic engine gave independence. Not absolute, not fairy tale independence, but practical independence. It allowed the aircraft to be built into an existing system of repair and supply. That meant that the Catalina in Soviet service stopped being a foreign miracle and became equipment that could be handled under local rules. That is how a foreign aircraft gradually lost its foreign status. The metal hull also played its part. For naval aviation, it was not decoration, it was endurance. Dampness, salt, temperature changes, storage near water, repeated takeoffs and landings from the surface, all of it quickly reveals who was built for the sea and who was merely pretending. The Catalina proved strong enough to enter that environment seriously. This applies to why the machine was valued not as an engineering trophy, but as working power. It could be used in different theaters, for different tasks, under different climatic conditions. It did not demand a perfect world around it. It was built for a world where everything is wet, heavy, distant, and inconvenient. In the Soviet fleet, these aircraft became the main flying boat. That says a great deal about the machine. Foreign designs are not kept in military service out of respect for a beautiful biography. They are kept if they solve a task, if they fly, if they can be maintained, if crews trust them, and if commanders understand why they need them. The Catalina solved exactly that kind of task. It could patrol, search, connect remote points, work over water, and fly missions where an ordinary aircraft was too dependent on an airfield. For the Soviet Navy, that was especially important. The country had enormous maritime spaces, but could not everywhere provide convenient infrastructure. This applies to the crude logic of service. A useful machine lives long, not because writers praise it, not because reports dress it in fine language, but because every year of service proves that it is still needed. Some Soviet aircraft remained in service until the end of the 60s. Almost 3 decades for an aircraft born in the age of drafting boards and hand calculations was not an accident. By then, aviation had moved far ahead. Jet aircraft had appeared, speeds had changed, requirements had changed, and military technology itself had changed. But flying boats of this type still found their place where range, water, and endurance mattered more than fashionable speed. That was the real blow to skeptics. The old design continued to serve not because of sentiment, but because of usefulness. That is how the Catalina became part of Soviet naval history, not as an American curiosity in foreign service, but as a machine that was studied, modified, mastered, and used where it was needed. There was no gloss in its Soviet biography. There was the Taganrog plant, Lend-Lease deliveries, domestic engines, salt water, naval units, and long service. And that makes the story harder than any legend. The aircraft proved its value not in advertising, but in the ranks. The aircraft already had range, a hull built for water, maritime endurance, serious naval interest, and the first signs of a large future service life. But it still did not have a name that could live in memory. It had an index. Cold, technical, almost lifeless. XP-3Y1. For engineers and staff paperwork, that was enough. For history, it was not. Military machines are often born under dry designations. Letters, ciphers, numbers, factory codes, modification indexes. They are useful for documents, orders, and reports. But such designations rarely become legends. They do not sound like the name of a machine. They sound like a line in an archive register. The aircraft still had to make the passage from technical code to a word the world would remember. This applies to the strange power of a name, which military organizations often underestimate. A good machine can serve under an index, but a legend almost always receives a name. A name is easier to say, easier to remember, easier to pass from pilot to pilot, from mechanic to mechanic, from fleet to fleet. The index remains in the files. The name enters living speech. In 1939, Europe was already standing at the edge of disaster. In London, they understood perfectly that the sea would again become a field of struggle, and that Britain, as an island power, would suffer without long-range patrol. German submarines, trade routes, convoys, distant approaches to the islands, all of this required eyes over the water. Ordinary aircraft were not enough for that task. The British Admiralty needed patrol flying boats. Not in theory, not someday, not after years of calm reflection. It needed them quickly, in numbers, with range, and with proven ability to work over the sea. Attention turned to the American Consolidated Machine, which had already shown that it was not an office promise, but a real maritime instrument. This applies to the moment when an aircraft stops being the private concern of its own country. If a foreign fleet wants it, its value has become visible beyond national pride and factory advertising. Britain was not buying a pretty legend. Britain was buying the ability to see farther over the ocean than older tools allowed. In that same year, the British ordered more than 100 of these flying boats. For Consolidated, this was not just a foreign contract. It was a loud signal. The machine was needed not only by the American Navy. It was needed by those who understood the price of sea communications, long-range search, and constant presence over water. The nameless aircraft had taken a step into an international life. But the British did something else to it. Not technical, not industrial, not connected to engines or hull. They gave it a name. And that mattered more than office men, trained to think in indexes, might have believed. The aircraft known in American paperwork by a dry designation became Catalina. The name was chosen after Santa Catalina Island off the coast of California. A small island not far from Los Angeles, rocky, surrounded by water, linked to the same coast where the Consolidated Machine had been born. There was a rough kind of precision in that choice. An aircraft created by the Pacific received the name of an island from that same world of water, rock, wind, and sea horizon. This applies to the rare case when a name does not feel like a random label. Catalina sounded softer than the military index, but behind that softer sound stood an iron machine. The name carried geography, sea air, a California trace, and a simplicity that XP-3Y1 did not have. The dry code remained for papers. Catalina began to live among people. The contrast was almost insulting. The Americans created the aircraft, brought it through testing, put it into production, but did not give it the name that would stick to it forever. The British did. A foreign fleet looked at the American flying boat and named it so well that the Americans themselves would begin using the name. That is one of the ironies of great technology. Sometimes a machine is christened not by those who built it. The name quickly proved useful. It could be spoken on a base. It could be written in an order. It could be remembered by a pilot, a mechanic, a radio operator, a staff officer. Catalina did not sound like a storage item or an experimental sample. It sounded like a machine with character. In military aviation, that is not a small thing. This applies to how a real reputation is born. First, a machine proves itself with figures. Then customers accept it. Then it receives a name, and that name starts moving separately from factory designations. At that moment, equipment leaves the narrow world of engineers and becomes part of military language. American documents could still carry dry designations, but in living speech, Catalina gradually won. Pilots and mechanics found it easier to say. Naval people have always tended to give machines names because they do not serve with numbers. They serve with heavy, demanding, dangerous, necessary equipment. If a machine goes out over the sea every day and returns, it quickly stops being a cluster of letters. By the beginning of the 1940s, the name had found its place. The world was entering a major war. Oceans were becoming battlegrounds, and Catalina already had not only a design, but a sound. That mattered. Very soon, this name would be spoken not in quiet trials and not in procurement offices, but on bases, in reports, in rescue operations, and along combat patrol routes. So the dry index gave way to a word that would outlive the documents. XP-3Y1 was needed by engineers. Catalina was needed by history. The British gave the machine its name, and the war made that name heavy. From this point on, it was no longer just a successful American flying boat. It was Catalina, a machine that received its voice before the world fully learned what it could do. On December 7, 1941, Pearl Harbor still looked calm. The morning in Hawaii gave no honest warning of the blow that would soon become one of the hardest pages of the Pacific War. Ships lay in the harbor, aircraft stood on the airfields, flying boats rested at their moorings. The water was almost still, and the base lived inside the dangerous confidence that the main threat was somewhere far away. Then Japanese aircraft appeared in the sky. That confidence collapsed at once. The attack came not as a warning, not as a demonstration, but as a calculated operation in which every target had a place. Battleships, airfields, fuel stores, vessels, aircraft. Japanese planners were not striking blindly. They knew what they wanted to remove from the board in the first minutes. This applies to the most important question. Why were Catalina moorings among the priority targets? Why did a slow-flying boat, nothing like a fierce fighter, appear in the same logic as battleships and airfields? The answer is uncomfortable for anyone who judges aircraft only by speed and guns. The Japanese did not fear its beauty or its sudden attack. They feared its eyes. Several dozen Catalinas stood on the water near the piers. From a distance, they looked like heavy machines, not as dramatic as frontline combat aircraft. But for the Japanese fleet, they were not secondary equipment. They were a direct threat to the entire operation. If those aircraft took off in time, they could move far out over the ocean, detect ships, send coordinates, and break the main weapon of the Japanese plan: surprise. The Catalina's range was about 4,800 kilometers. In the Pacific, that was not just a technical virtue. It meant that an aircraft based in Hawaii could spend hours sweeping vast areas of water, looking for what the enemy wanted to hide beyond the horizon. A fleet planning to approach unseen has a special hatred for machines that can see farther than others. This applies to the logic of naval war. A battleship is dangerous because of its guns. An aircraft carrier is dangerous because of its strike aircraft. A submarine is dangerous because of concealment. But a long-range patrol aircraft is dangerous in another way. It can strip the enemy of secrecy. Without secrecy, a surprise operation begins to crack before the first blow is delivered. By that time, some Catalinas were already receiving radar. That made them even more dangerous. The human eye can be deceived by darkness, fog, rain, and haze over water. Radar is harder to deceive. It turns night and bad weather from shelter into inconvenience, not into a guarantee of safety. For a Japanese task force, that was a serious problem. That is why the attack on the flying boat moorings was not accidental cruelty and not a side target. It was calculation. Destroying Catalinas on the water was more useful than waiting for them to climb into the sky and begin searching for the fleet. On the surface, even the most useful aircraft is vulnerable. In the air, it becomes a problem every staff must consider. This applies to a recognition the enemy made without speeches. No Japanese officer had to deliver praise for the Catalina. The target list was enough. If a machine is attacked in the first minutes of a major operation, its importance has been understood. Sometimes the most honest evaluation of military technology comes not from friends, but from those who want to deprive you of it first. At Pearl Harbor, the Catalinas lost precious time and precious metal. Several machines were damaged or put out of action, and with them the fleet lost part of its long-range eyes over the ocean. But the attack itself proved something important. This flying boat had long since stopped being a supporting detail. It had become part of a system without which a huge maritime war turned into blind movement across a map. The Japanese understood that the Catalina did not need to fight fighters to be dangerous. It did not need to shoot anything down. It only had to find. It only had to send coordinates. It only had to raise the alarm before the strike force reached a comfortable distance. In a war built on concealment, one detecting aircraft could spoil the entire plan. This applies to the main force of reconnaissance aviation. It rarely looks spectacular to the public. It does not always produce loud images, and it does not always provide an easy, heroic picture. But it answers the question every fleet faces: who sees whom first? On the ocean, that question is often more important than armor thickness or gun caliber. After the attack, the importance of the Catalina could no longer be dismissed as secondary service. If the enemy attacks your eyes, he is afraid of being seen. If he strikes patrol flying boats alongside battleships, he is placing them among the forces that can ruin an operation. This is not decoration and not legend building. This is the logic of combat planning. That is where the mistake of skeptics becomes especially clear. They looked at the Catalina as slow, old-fashioned, almost awkward. Yes, it was not the predator of air combat. Yes, it did not carry the image of a fast strike. But in the Pacific, the more dangerous machine was sometimes not the one that fired first. It was the one that saw first and reported. Pearl Harbor became a dark recognition of its value. The enemy showed that he understood what the Catalina was worth. Not with congratulations, not with reports, not with medals, but with strikes on its moorings. From that moment, the Catalina entered the war not as a strange flying boat for distant routes, but as a machine that opponents wanted neutralized before takeoff. Because after takeoff, it could see too much. After Pearl Harbor, the Catalina could no longer remain a second-line machine. The Pacific demanded eyes, range, and patience, not only loud attacks and polished reports. On a map, that ocean looks like a blue space, but for a fleet it was a huge zone of uncertainty. Ships vanished there, routes were lost, submarines hid, convoys moved, and the horizon deceived every man who thought he could see far enough. The Catalina became the aircraft that expanded the fleet's sight. It rose from water or from a coastal base, went out on long routes, and worked for hours over the sea when ordinary aircraft were already counting fuel. Its strength was not a spectacular rush. Its strength was stubborn presence. It could remain over the ocean, search, compare, report, search again, and refuse to leave just because the work was monotonous. This applies to the kind of war where the loudest machine does not always matter most. A battleship can fire a heavy salvo, an aircraft carrier can launch a strike group, but all of them need one thing first: to know where the enemy is. Without reconnaissance, a fleet becomes an expensive blind mass. The Catalina gave it sight. Huge areas of the Pacific became daily work for its crews: water, clouds, rain, fog, sunlight on waves, gray lines of swell, barely visible shapes at the edge of vision. They had to distinguish an empty horizon from a ship's trace, an ordinary spot from a periscope, a harmless line on the water from the route of a submarine. A mistake could cost a convoy too much. Radar strengthened that work. Night was no longer reliable shelter. Fog no longer gave the same confidence. Bad weather stopped being a loyal ally of those who wanted to hide. The Catalina, with long range and radar search, turned empty ocean into observed space, and for the enemy, that was worse than many louder threats. This applies to the aircraft's central role in the Pacific. It was not fleet decoration and not a spare aircraft for quiet days. It was a scout, a guard, a messenger, and an alarm bell over water. If it found a target, the work of ships, strike aircraft, and headquarters began. But the Catalina had another service, one that made men speak of it not only with respect, but with real gratitude. It did not only search for the enemy, it searched for its own. When a pilot, after a forced landing or a brutal air fight, found himself in a life vest in the middle of the ocean, the silhouette of this flying boat could mean the difference between return and the empty silence of water. Picture it without decorative heroics. A man in the ocean. Depth beneath him, salt water around him, heat or rain above him, perhaps an inflatable raft if luck had not completely abandoned him. No shore in sight, no ship in sight. Time stretches cruelly, skin burns, lips dry out, strength drains away, and the horizon remains empty. In that situation, performance figures no longer matter. Only one thing matters. Will they find him or not? This applies to the rescue operations unofficially known as Dumbo. The name sounded almost absurd in a hard war, but behind it stood deadly serious work. The Catalina received coordinates, moved into the search area, and began combing the water. Finding one man in the vast ocean was not a pretty episode. It was an insultingly difficult task. From above, a man on the water is a tiny point. A wave can hide him in a second. Sun glare blinds the eye, fog cuts visibility, rain turns the surface into gray confusion. The navigator calculates the route, lookouts stare until their eyes ache, the radio operator keeps contact, and the pilots fly the search pattern. All of this often happened far from base, where even a course error could eat away the last chances. When the survivor was found, the second and heavier part began. The Catalina could do what most aircraft simply could not: land on the water beside him. Not on a calm lake for a fine photograph, but on the ocean surface where waves have their own will. The pilot judged wind direction, wave height, speed, and approach angle, and had to put the large machine down without breaking the hull or losing sight of the man. This applies to a level of skill that dry reports rarely show. Landing on the ocean means dealing not with a runway, but with a moving force. Too hard, and the hull takes the blow. Too late, and the man is left behind. Too cautious, and there may not be enough space or time. In those minutes, the Catalina was no longer just an aircraft. It became a boat, a shelter, and a final hope. After landing, the crew brought the man to the side, lifted him aboard, gave him water, warmth, help, and above all returned him from the loneliness of the ocean to the world of people. Then the aircraft had to take off again. With extra weight, waves under the hull, risk, and the heavy run for which it needed powerful engines, the right hull, and all of its maritime construction. There are aircraft that destroy, and there are aircraft that bring men home. The Catalina was one of those machines. Headquarters valued it for range, commanders for reconnaissance, mechanics for serviceability, but the airmen it pulled from the ocean remembered something else: the low silhouette over water, the drone of engines, the circle over the search area, and the moment they knew they had been seen. That is why affection for the Catalina was not a newspaper invention. It was not born from posters, but from rescued men, long searches, water landings, and crews who risked themselves for those who had almost been left alone with the ocean. In war, that kind of reputation cannot be assigned by order. It can only be earned. The Catalina was trusted with more than patrol routes and search grids. It was trusted with people, cargo, negotiations, and flights that ordinary reports described carefully, as if too much clarity might disturb the truth. War loves the loud names of ships and generals, but the real work often rests on machines that simply do what others cannot. The Catalina became exactly that kind of machine. Not a parade aircraft, but a tool for missions where one mistake could break a diplomatic calculation or leave men without help over a vast stretch of water. In 1941, President Franklin Roosevelt sent his personal representative, Harry Hopkins, to the Soviet Union. This was not an ordinary official, not a random envoy with a briefcase and a polite smile. In Washington, Hopkins was called the president's shadow because he stood close to the most important decisions. When such a man is sent across dangerous wartime routes, the aircraft is not chosen for the comfort of its cabin. This applies to a level of trust that advertising cannot buy. Such a flight required range, survivability, and freedom from ordinary runway dependence. The Catalina could land on water, travel far, hold its route, and give its crew options where another aircraft became hostage to airfields. The logic was brutally simple. The less dependence on land, the greater the chance of completing the mission. Hopkins reached Moscow, and the talks on supply gained a different weight. Lend-lease was not a pretty classroom term. It was a massive system of equipment, materials, obligations, and future payments. Behind it stood factories, fronts, ships, railroads, ports, and decisions that could not be handled through polite letters alone. The president's own man was needed, and so was an aircraft trusted to carry him. On the return route, the story gained a harder edge. A valuable cargo was carried aboard, platinum, transferred by the Soviet side as part of payment arrangements for supplies. Imagine not a bank vault, not an armored convoy, not guards at heavy doors, but a flying boat above water. Beneath it lay thousands of kilometers of route, around it ocean and weather, and inside it metal for which states paid not in speeches, but in real value. This applies to the side of war where romance disappears completely. Diplomacy, money, technology, and risk traveled inside one hull. Here, the Catalina was not a pretty legend. It was reliable transport for a delicate mission. If an aircraft is chosen for such a flight, its value has already moved far beyond patrol duty. After the war, many machines met a short and rough fate. Some were written off quickly, some were cut for metal, others were pushed into distant corners of bases, but the Catalina was too useful to vanish immediately after the final shots, especially in places where sea, fog, distant coasts, and the lack of convenient airfields had not gone anywhere. In the Soviet Union, these aircraft continued to serve for a long time. In the Far East, with the Pacific Fleet, they were still flying missions, while aviation itself was changing rapidly. The jet age was advancing, speeds were rising, requirements were different, but the old flying boat still had work to do. Water does not ask whether your aircraft is fashionable. Water asks whether it can take off, land, and return. This applies to Sukhodol Bay in Primorsky Krai. There, not far from Vladivostok, traces of that service remain. Piers, slipways, taxi routes, and old infrastructure designed specifically for flying boats. Concrete and metal outlasted men, orders, aircraft changes, and entire periods of history. Such traces are unpleasant for those who like to say history lives only in books. No, sometimes it lies directly by the water. Veterans of the unit still remembered these machines in the 1980s, not as foreign American products, but as their own working boats. They remembered the sound of the engines, the behavior of the hull on water, fog over the Sea of Japan, long flights, and return to the bay. That kind of memory does not form around useless equipment. It remains only around machines that spent years doing dirty, heavy, necessary work. Then the Catalina moved into civilian life. After the war, thousands of flying boats ended up not with headquarters, but with civilian operators, expeditions, carriers, firefighting services, private owners, and aviation enthusiasts. Around 3,600 machines moved into different countries and continents. Europe, Latin America, South Africa, Australia. Wherever there was water and not enough runways, this design found work again. This applies to a rare quality of a true machine. It outlives war because it is useful beyond war. The Catalina could carry cargo, work in remote regions, support expeditions, and land on water where an aircraft with ordinary landing gear was helpless. First, the fleet demanded it. Then peaceful service took it. That was not a fall in status. It was proof of the strength of the design. In the United States, individual Catalinas survived especially long because of private aviation culture and the stubbornness of people who refused to turn living history into a motionless exhibit. Enthusiasts keep these machines alive, search for parts, repair engines, protect hulls, and fly them at air shows. It is expensive, difficult, inconvenient, and not at all a rational business. But without such people, these aircraft would fall silent forever. And here is the final paradox. An aircraft created in the age of pencils, drafting boards, and hand calculations can still rise above water. Not as an image in a museum, not as a dusty label behind glass, but as a real machine with working engines. Evening sky, dark water, slow takeoff run, heavy drone of radial engines, and the silhouette of the Catalina rises over the shore again. This applies to the last and most honest proof of its legend. A machine can be praised in books, decorated with loud words, and argued over in specifications and variants. But if, after decades, it can still fly, then its engineers reached the core of the problem. The Catalina was not the fastest aircraft of the war, but it became one of those machines that saw the ocean, brought men back, served great powers, outlived its age, and remained in the sky. And this is the main paradox of the Catalina. It was not the fastest. It was not the most frightening to look at. It did not tear through the sky like a fighter, and it did not crush the imagination like a heavy bomber. But it was trusted with the ocean, with men, with secret flights, with platinum, with long searches, with rescue missions, with routes where mistakes were not forgiven. The Catalina did not disappear into history as a dead museum shell. It left traces in bays, on old slipways, in the memories of crews. And even today, some of these machines can still rise into the sky. So here is the question. What do you think? Was the Catalina truly an underestimated genius of naval aviation? Or was its legend created not by design, but by the war itself, because the fleet simply had no better choice? Write your version in the comments. Especially if you understand one thing, the real strength of a machine is not always in speed and guns. Leave a like if you want more archive stories without polished parade myths. Subscribe to the channel and turn on the bell, so you do not miss the next episodes about machines that changed war, but remained in the shadows for far too long.